In this video, we're going to be solving a whole collection of trigonometric equations. Now, because it's the technique of solving the equation and in ensuring that we get enough solutions that's important and not actually looking up the angle, all of these are designed around certain special angles. So I'm just going to list at the very beginning here the special angles and their sines, cosines and tangents that are going to form the basis of what we're doing. So the special angles that we're going to have a look at are 0, 30, 45, 60 and 90. They're in degrees. If we're thinking about radians, then there's 0, pi by 6, pi by 4, pi by 3, and pi by 2. The trig ratios we're going to be looking at are the sine, the cosine, and the tangent of each of these. The sine of 0 is 0. The sine of 30 is a half. Sine of 45 is 1 over root 2. The sine of 60 is root 3 over 2. And the sine of 90 is 1. Cosine of 0 is 1. Cosine of 30 is root 3 over 2. The cosine of 45 is 1 over root 2. The cosine of 60 is a half, and the cosine of 90 is 0. The tan of 0 is 0. The tan of 30 is 1 over root 3. The tan of 45 is 1. The tan of 60 is root 3. And the tan of 90 degrees is infinite. It's undefined. It's these that we're going to be looking at and working with. Let's look at our first equation then. We're going to begin with some very simple ones. So we'll take sine of x is equal to 0.5. Now invariably when we get an equation, we get a range of values along with it. So in this case, we'll take x is between 0 and 360. So what we're looking for is all the values of x whose sine gives us 0.5. Let's sketch a graph of sine x over this range. And sine looks like that, with 90, 180, 270 and 360, and ranging between 1 for sine 90 and minus 1 for the sine of 270. Sine of x is 0.5, so we go there and there. So there's our first angle and there's our second angle. We know the first one is 30 degrees because sine of 30 is a half. So our first angle is 30 degrees. This curve is symmetric. And so because we're 30 degrees in from there, this one's got to be 30 degrees back from there. And that would make it 150. There are no more answers because within this range, as we go along this line, it doesn't cross the curve at any other points. Let's have a look at a cosine. Cos of x is minus 0.5. And the range for this, x between 0 and 360. So again, let's have a look at a graph of the function involved in the equation. And the cosine graph looks like that. 1 and minus 1. This is 90, 180, 270, and then here at the end 360. Minus 0.5. Again, across there at minus 0.5 and down to there and down to there. Now the one thing that we do know is that the cos of 60 is plus 0.5, and so that's there. So we know there is 60. Now again, this curve is symmetric. So if that one is 30 back that way, this one must be 30 further on. So our first angle must be 120 degrees. And this one's got to be in a similar position, because this bit of the curve is again symmetric. So that's 270, and we need to come back 30 degrees, so that's 240. Now we're going to have a look at an example where we've got what we call a multiple angle. So instead of just being cos of x or sine of x, it's going to be something like sine of 2x or cos of 3x. So let's begin with sine of 2x is equal to root 3 over 2. And again, we'll take x to be between 0 and 360. Now, we've got 2x here. So if we've got 2x and x is between 0 and 360, then the total range that we're going to be looking at is 0 to 720. 2x is going to come between 0 and 720. And the sine function is periodic. It repeats itself every 360 degrees. So I'm going to need 2 copies of the sine curve. There's the first one going up to 360, and now I need a second copy there going on to 720. Okay, so sine 2x equals root 3 over 2. Well, we know that the sine of 60 is root 3 over 2. So if we put in root 3 over 2, it's there. Then it's going to be these along here as well. So what have we got? Well, the first one here we know is 60. This point we know is 180, so that one's got to be the same distance back in due to the symmetry, 120. So we do know that 2x will be 60 or 120. But we also know we've got these other points on here. So let's just count on where we are. There's the first loop of the sine function, the first copy. It's periodic and repeats itself again. So now we need to know where are these. Well, this is an exact copy of that. So this must be 60 further on, in other words, at 420. And this must be another 120 further on, in other words, at 480. So we've got 2 more answers. And it's x that we actually want, not 2x. So this is 30, 60, 210, and finally 240. Let's have a look at that with a tangent function this time. Tan of 3x is equal to minus 1. And we'll take x to be between 0 and 180. So we'll draw a graph of the tangent function. So we go up, and we've got that there, that's 90. And this is 180, and this is 270. Now it's 3x. x is between 0 and 180, so 3x can be between 0 and 3 times 180, which is 540. So I need to get copies of this using the periodicity of the tangent function right up to 540. So let's put in some more. That's 360. And on there, that's 450. This one here will be 540. And that's as near or as far as we need to go. Tan of 3x is minus 1. So here's minus 1. And we go across here, picking off all the ones that we need. So we've got one there, there, there. These are our values. So 3x is equal to... Now we know that the angle whose tangent is 1 is 45, which is there. So again, this and this are symmetric bits of curve. So this must be 45 further on. In other words, 135. This one here has got to be 45 further on. So that will be 315. This one here has got to be 45 further on, so that will be 495. But it's x that we want, not 3x, so let's divide throughout by 3. So 3's into that is 45, 3's into that is 105, and 3's into that is 165. And those are our three answers for that one. 45 degrees, 105 degrees, and 165. Let's take cos of x over 2 this time. So instead of multiplying by 2 or by 3, we're now dividing by 2. Let's see what difference this might make. Equals minus a half. And we'll take x to be between 0 and 360. So let's draw the graph of cos x between 0 and 360. So there we've got it, 360 there, 180 there, and we've got 90 and 270 there and there. Minus a half. Now that's going to be there, across, and then these are the ones that we are after. So let's work with that. X over 2 is equal to... Now, where are we? Well, we know that the angle whose cosine is a half is in fact 60 degrees, which is here, 30 in from there. So that must be 30 further on, in other words, 120. And this one must be 30 back, in other words, 240. So now we multiply up by 2 and we get 240 and 480. But of course, this one is outside the given range. The range is 0 to 360, so we do not need that answer. We just want the 240. Now, we've been working with a range of 0 to 360, or in one case, 0 to 180. So let's change the range now so it's a symmetric range in the y-axis. So the range is now going to run from minus 180 to plus 180 degrees. So we'll begin with sine of x equals 1, and x is to be between 180 degrees but greater than minus 180 degrees. Let's sketch the graph of sine in that range. So we want a complete copy of it. It's going to look like that. Now we know that the angle whose sine is 1 is 90 degrees. And so we know that's 1 there and that's 90 there. And we can see that there is only the one solution. It meets the curve once and once only. So that's 90 degrees. Once and once only, that is, within the defined range. Let's take another one. So now we'll use a multiple angle, cos 2x equals a half, and we'll take x to be between minus 180 degrees and plus 180 degrees. So let's sketch the graph. Let's remember that if x is between minus 180 and plus 180, then 2x will be between minus 360 and plus 360. So what we need to do is use the periodicity of the cosine function to sketch it in the range. So there's the 0 to 360 bit, and then we want to minus 360. So let's just label up the points. Here is 90, 180, 270, 360, and then back this way, minus 90, minus 180, minus 270, and minus 360. Now, cos 2x is a half. So here's a half, remembering that this goes between plus 1 and minus 1. And if we draw a line across to see where it meets the curve, then we can see it meets it in 4 places. There, 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 and there. We know that the angle where it meets here is 60 degrees. So our first value is 2x equals 60 degrees. By symmetry, this one back here has got to be minus 60. What about this one here? Well, again, symmetry says that we are 60 from here, so we've got to be 60 back from there, so this must be 300. And our symmetry of the curve says that this one must be minus 300. And so we have x is 30 degrees, minus 30 degrees, 150 degrees, and minus 150 degrees. Working with the tangent function, tan 2x equals root 3. And again, we'll place x between 180 degrees and minus 180 degrees. We want to sketch the function for tangent, and we want to be aware that we've got 2x. So since x is between minus 180 and plus 180, 2x has got to be between minus 360 and plus 360. So if we take the bit between naught and 360, which is that bit of the curve, we need a copy of that between minus 360 and 0, because again the tangent function is periodic. So we need this bit. So we need that. And we need that. And let's mark off this axis so we know where we are. This is 90, 180, 270, and 360. So this must be minus 90, minus 180, minus 270, and minus 360. Now 2x is root 3. The angle whose tangent is root 3 we know is 60. So we go across here at root 3 and we meet the curve there and there. And we come back this way and we meet it there and we meet it there. So our answers are down here. Working with this one first, we know that that is 60. So 2x is equal to 60. And so that one is 60 degrees on from that point. Symmetry says, therefore, this one is also 60 degrees on from there. In other words, it's at 240. Let's work our way backwards. This one must be 60 degrees on from minus 180. So it must be at minus 120. And this one is 60 degrees on from minus 360. And so therefore it must be minus 300. And so if we divide throughout by 2, we have 30, 120, minus 60, and minus 150 degrees. We want to put degree signs on all of these. So there are 4 solutions there. Trig equations often come up as a result of having expressions or other equations which are rather more complicated than that and depend upon identities. So I'm going to have a look at a couple of equations. These equations both depend upon 2 identities. That is, expressions involving trig functions that are true for all values of x. So, the first one is sine squared of x plus cos squared of x is 1. This is true for all values of x. The second one we derive from this one. How we derive it doesn't matter at the moment, but what it tells us is that sec squared x is equal to 1 plus tan squared x. So these are the 2 identities that I'm going to be using. Sine squared x plus cos squared x is 1, and sec squared of x is 1 plus tan squared of x. Okay. So how do we go about using one of those to do an equation like this? Cos squared x plus cos of x is equal to sine squared of x, and x is between 180 and 0 degrees. Well, we've got a cos squared, a cos, and a sine squared. If we were to use our identity, sine squared plus cos squared is 1, to replace the sine squared here, I'd have a quadratic in terms of cos x. And if I got a quadratic, then I know I can solve it either by factorising or by using the formula. So let me write down sine squared x plus cos squared x is equal to 1, from which we can see that sine squared of x is equal to 1 minus cos squared of x. So I can take this and plug it into there. So my equation now becomes cos squared x plus cos x is equal to 1 minus cos squared x. Now I want to get this as a quadratic. Square term, linear term, constant term equals 0. So I begin by adding cos squared to both sides. So adding on a cos squared there makes 2 cos squared x plus cos x equals 1, because I added cos squared to get rid of that one. Now I need to take 1 away from both sides. 2 cos squared x plus cos x minus 1 equals 0. And now this is just a quadratic equation. So the first question I've got to ask is, does it factorise? So let's see if we can get it to factorise. I'll put 2 cos x in there and cos x in there, because that 2 cos x times that cos x gives me 2 cos squared, and I'll put a 1 and a 1 there, because 1 times by 1 gives me 1, and now I know to get a minus sign, 1's got to be minus and 1's got to be plus. Now I want plus cos x, so if I make this one plus, I'll have 2 cos x times by 1 is 2 cos x. If I make this one minus, I'll have minus cos x from there. Taking those two together, plus 2 cos x minus cos x is going to give me the plus cos x in there. So that equals 0. Now, if that equals 0, I'm multiplying two numbers together, this one, 2 cos x minus 1, and this one, cos x plus 1. So one of them, or both of them, have got to be equal to 0. So 2 cos x minus 1 is 0, or cos of x plus 1 is 0. So this one tells me that cos of x is equal to a half, and this one tells me that cos of x is equal to minus 1. And both of these are possibilities. So I've got to solve both equations to get the total solution to the original equation. So let's begin with this. Cos of x is equal to a half. And if you remember, the range of values was 0 to 180 degrees. So let me sketch cos of x between 0 and 180 degrees. And it looks like that. 0, 90, 180. We go across there at half and come down there. And there is only one answer in the range. So that's x is equal to 60 degrees. For this one, again, let's sketch cos of x between 0 and 180. That's there and there, between minus 1 and plus 1. And we want cos of x equal to minus 1 just at one point there. And so therefore x is equal to 180 degrees. So those are our two answers to the full equation that we had. So let's now have a look at 3 tan squared x is equal to 2 sec squared x plus 1. And this time we'll take x to be between 0 and 180 degrees. Now, the identity that we want is obviously the second one of the two that we had before. In other words, the one that tells us that sec squared x is equal to 1 plus tan squared x. And we want to be able to take this 1 plus tan squared and put it into there. So we've got 3 tan squared x is equal to 2 times 1 plus tan squared x plus 1. Multiply out this bracket. 3 tan squared x is 2 plus 2 tan squared x plus 1. We can combine the 2 and the 1. That will give us 3. And we can take the 2 tan squared x away from the 3 tan squared x there. And that will give us tan squared x. And now we take the square root of both sides. So we have tan x is equal to plus root 3 or minus root 3. And we need to look at each of these separately. So, tan x equals root 3 and tan x equals minus root 3. X is to be between 0 and 180. So let's have a sketch of the graph of tan between those values. So there is 90 and there is 180. The angle whose tangent is root 3 we know is there at 60. So we know that x is equal to 60 degrees. Here we've got minus root 3. So again, little sketch. Between 0 and 180, the range over which we're working. Here we've got minus root 3. Go across there and down to there. And symmetry says it's got to be the same as this one over here. It's got to be the same either side. So in fact, if that was 60 there, this must be 120 here. So x is equal to 120 degrees. So far we've been working in degrees, but it makes little difference if we're actually working in radians. And let's just have a look at one or two examples where, in fact, the range of values that we've got is in radians. So if we take tan x is minus 1, and we take x to be between plus or minus pi. Another way of looking at that would be, if we were in degrees, it would be between plus and minus 180. Let's sketch the graph of tangent within that range. Up to there, that's pi by 2. And up to there, which is pi. Minus pi by 2. And there, minus pi. Tan of x is minus 1. So somewhere across here, it's going to meet the curve. And we can see that it meets it here and here, giving us these solutions at these points. Well, we know that the angle whose tangent is plus 1 is pi by 4. So this must be pi by 4 further on. And so we have x is equal to pi by 2 plus pi by 4. That will be 3/4 of pi, or 3 pi by 4. And this one here must be minus pi by 4 back there. So minus pi by 4. Let's take one with a multiple angle. So we'll have a look at cos of 2x is equal to root 3 over 2. And we'll take x between 0 and 2 pi. Now, if x is between 0 and 2 pi, and we've got 2x, then that means that 2x can be between 0 and 4 pi. So again, we've got to make use of the periodicity of the graph of cosine to get a second copy of it. So there's the first copy between 0 and 2 pi, and now we want a second copy that goes from 2 pi up to 4 pi. And we can mark these off. That one will be pi by 2, pi, 3 pi by 2. This one will be 5 pi by 2. This one 3 pi, and this one 7 pi by 2. So, where are we with this? Cos 2x equals, well, in fact, we know cos 2x is root 3 over 2. We know that the angle that gives us the cosine that is root 3 over 2 is pi by 6. So our first one is pi by 6. Root 3 over 2 up here. We go across, we meet the curve, we come down. We know that this one here is pi by 6. Let's keep going across the curves and see where we come to. Well, we come to one here, which is pi by 6 short of 2 pi. So let me write it down as 2 pi minus pi by 6. And then again we come to one here. Symmetry suggests it should be pi by 6 further on. So that's 2 pi plus pi by 6. And then this one here is symmetry would suggest is pi by 6 short of 4 pi. So 4 pi minus pi by 6. So let's do that arithmetic. 2x is pi by 6. Now, how many sixths are there in 2? Well, the answer is there are 12 of them, and we're going to take one of them away. So that's 11 pi by 6. We're going to now add a sixth on. So that's 13 pi by 6. How many sixths are there in 4? Well, there are 24 of them, and we're going to take one away. So that's 23 pi over 6. And now we want x, so we divide each of these by 2. Pi by 12, 11 pi by 12, 13 pi by 12, and 23 pi by 12. And there are our 4 solutions. Let's have a look at one where we've got the x divided by 2 rather than multiplied by 2. So the sine of x over 2 is minus root 3 over 2. And let's take x to be between pi and minus pi. So we'll sketch the graph of sine between those limits. So it's there and there. Pi, 0 and minus pi. We're looking for minus 3 over 2. Now the one thing we do know is that the angle whose sine is 3 over 2 is pi by 3. But we want minus root 3 over 2, so that's down there. We go across and we meet the curve at these 2 points. Now this curve is symmetric with this one. So if we know that at plus root 3 over 2 this one was pi by 3, then we know that this one must be minus pi by 3. This one is pi by 3 back, so it's at 2 pi by 3, so this one must be at minus 2 pi by 3. And so we have x over 2 is equal to minus 2 pi by 3 and minus pi by 3. But it's x that we want, so we multiply up. X equals minus 4 pi by 3 and minus 2 pi by 3. Let's just check on these values. How do they fit with the given range? Well, this one, minus 2 pi by 3, is in that given range. This one is outside, so we don't want that one. A final example here, working with the idea again of using those identities, and we'll take 2 cos squared x plus sine x is equal to 1, and we'll take x between 0 and 2 pi. We've got cos's and sines, so the identity that we're going to want to help us will be sine squared plus cos squared x equals 1. Cos squared here, let's use this identity to tell us that cos squared x is equal to 1 minus sine squared x, and make the replacement up here for cos squared. Because that, as we will see when we do it, leads to a quadratic in sine x. So let's multiply this out. 2 minus 2 sine squared x plus sine x is equal to 1. And I want it as a quadratic, so I want positive square term and then the linear term and then the constant term. So I need to add this to both sides. So 0 equals 2 sine squared x adding it to both sides. Now I need to take this away, minus sine x from both sides, and I need to take the 2 away from both sides. So 1 take away 2 is minus 1. And now, does this factorise? It's clearly a quadratic. Let's look to see if we can make it factorise. 2 sine x and sine x, because multiplied together, these two will give me 2 sine squared. 1 and 1, because multiplied together, these two will give me 1. But one of them needs to be minus to make this a minus sign here. So I think I'll have minus there and plus there, because 2 sine x times by minus 1 gives me minus 2 sine x. 1 times by sine x gives me sine x, and if I combine sine x with minus 2 sine x, I get minus sine x. I have 2 numbers multiplied together. This number, 2 sine x plus 1, and this number, sine x minus 1. They multiply together to give me 0. So one or both of them must be 0. So let's write that down. 2 sine x plus 1 is equal to 0, and sine x minus 1 is equal to 0. So this tells me that sine of x is equal to, take 1 away from both sides and divide by 2, so sine x is minus a half, and this one tells me that sine x is equal to 1. And I'm now in a position to solve these 2 separate equations. So let me take this one first. Now, we were working between 0 and 2 pi. So we'll have a sketch between 0 and 2 pi of the sine curve. And we want sine x equals 1. Well, there's 1, and there's where it meets, and that's pi by 2. So we can see that x is equal to pi by 2. Sine x equals minus a half. Again, the range that we've been given is between 0 and 2 pi. So let's sketch between 0 and 2 pi. There's 2 pi, 3 pi by 2, pi by 2, and 0. We want minus a half, so that's coming along between minus 1 and plus 1. That's going to come along there and meet the curve there and there. Now, the one thing that we do know is the angle whose sine is plus a half is pi by 6. So if we're looking at plus a half, it would be there, and it would be pi by 6. So it's pi by 6 in from there. So symmetry tells us that this must be pi by 6 in from there. So we've got x is equal to pi plus pi by 6, and symmetry tells us it's pi by 6 in from there, 2 pi minus pi by 6. There are 6 sixths in pi, so that's 7 pi by 6. There are 12 sixths in 2 pi. We're taking one of them away, so that will be 11 pi over 6. So we've shown there how to solve some trig equations. The important thing is to sketch the graph, find the initial value, and then work out where the others are from the graphs. Remember, the graphs are all symmetric and they're all periodic. So they repeat themselves every 2 pi or every 360 degrees.